Hello, my name is Grace O'Connell. I'm a professor here at UC Berkeley in mechanical engineering. And in this module, I'll be talking about viscoelasticity. It's broken up into 5 separate parts. The learning objectives for this module is to first introduce students to viscoelastic materials, some of the mechanical behaviors of these materials. Then we'll talk about 3 of the most commonly used linear viscoelastic models to describe the phenomenon seen during creep behavior. In the more advanced modules, I'll actually go through the derivation of the models and discuss how we can apply these models for recovery behavior and understanding loading history. And then lastly, I'll talk about nonlinear viscoelastic materials and how this is applied more specifically for biological materials that have a nonlinear elastic response. So in much of our discussion about materials, we largely focus on linear elastic materials. And these materials very much act like springs, where if we apply a force, a linear response is seen with displacement. And we can use Hooke's law to describe this behavior, where the force applied is equivalent to the spring stiffness times the displacement. We've talked about multiple types of material deformations in our materials class, where we can have elastic and plastic deformations that have been discussed. So when we think about this, in our elastic plastic deformations, we have our stress strain response, we have this elastic region, and then followed by a plastic region. So this response here, where everything is nice and linear, is linear related. We can use Hooke's law. However, in this plastic deformation region, it's very difficult to use a nice simple mathematical equation to describe this response. And so we rely on numerical methods to describe this behavior. And the third type of material deformation that we'll be talking about is creep deformations. These are deformations that are time dependent. So if we apply a load or we apply a displacement, the response will actually change from the point that we're looking at it now, and if we were to come back an hour from
now. It's funny with you in the room. In this video, I'm going to demonstrate how we can change the viscosity of a viscoelastic material with materials that we can find in our kitchen. So here I have regular honey, and we can see that it is quite viscous, and as it drips down, under its own weight, pulling down on the spoon. So again, we can see how quickly it's able to flow. It doesn't flow as quickly as water might, which is less viscous than the honey would be. I'm going to change the viscosity of this honey by putting it in the refrigerator for a period of time and letting it cool down and becoming more solid-like. Okay, my honey's been sitting in the fridge for what I think is about half an hour, and we'll see if the viscosity has changed. So you can see that it's moving a little bit slower than it was when it was at room temperature. A lot more viscous as a material. So all materials are very dependent on the temperature. And in the case of viscoelastic materials, we see that our material ranges from being more viscous or more elastic, depending on that temperature.
In creep deformations, we're talking about time-dependent responses. Now, we start with the materials that we're more familiar with, how they might respond in creep. If we apply a load and we hold it, we know that we're going to get a certain displacement. So we apply a force at some rate by newtons per second, and we're going to get an output. Our reading, our output will be displacement. So we refer to this as being force controlled because our force is our input. Similarly, on the instron, we could, or the MTS, whatever our mechanical testing device is, we could tell the machine to move to a certain displacement at a certain rate of millimeters per second, and our output would be a force, and we would call this as displacement controlled. And so if we were to hold this force or this displacement for a period of time, we're going to see the same output reading from a linear elastic material. Nothing will change over time. So it's a relatively boring experiment to run. It should be. However, if we're looking at viscoelastic materials that experience creep deformations, if we run the same type of experiment, so if we're running creep, we're going to apply a force or a stress if we normalize the force, and we hold it for a set period of time. What we're going to see from that is our output is our strain, our displacement from the machine, will have a sudden increase, and then it will continue to gradually increase over time. And this response here is our creep deformation, our time-dependent deformation. For stress relaxation, on the flip side, we would apply a deformation and we would hold that deformation for a set period of time. And our output from that, our reading from that would be the stress, how the stress changes with time. So our initial response would be a spike in the stress, and then this stress would relax over time. So to look at this more graphically, I created a bridge with an elephant on our bridge. So let's suppose that we made a bridge. For some reason, we made it out of polymers, plastic materials, which tend to be viscoelastic in nature. So if we think about a creep behavior where we're applying a load, we have an elephant that's crossing the bridge, but this elephant decides to just hang out in the middle of this bridge for a certain period of time. There will be an initial deformation from the weight of the elephant, and as the elephant hangs out in the middle of the bridge will continue to deform over time. And it could possibly deform so much that it eventually will break. This is our creep deformation, load dependent. For stress relaxation, this is something where we're applying a load or a strain and we're holding that strain. So for this example, our elephant would actually have to be underneath the bridge, pushing the bridge up a certain deformation or a certain displacement and holding that, staying constant under the bridge. So initially, we're going to have this spike in the stress that is read out by the material, our polymer bridge material, but eventually those stresses in that material will relax out. It may relax to a equilibrium point where it flattens out, or some materials may actually relax down to zero in a fully relaxed state. So there's two approaches that are used for solving these complex behaviors that we see. We can use constitutive equations, which are essentially mathematical equations that describe these complex stress strain behaviors. An example of a simplified constitutive equation or mathematical equation would be Hooke's law, where we use that for linear elastic materials. So essentially what we're saying is we have some type of stress response to applied strain, and we're going to describe this with a function. And then once we know what this function is, we can then actually apply this to finite element models that will allow us to evaluate and visualize 3D stress strain responses. However, many of the constitutive models do not account for time-dependent behavior, many of the hyperelastic type of constitutive models. So what we're talking about here when we're discussing our linear viscoelastic models are rheological models. These are the simplest models to describe the mechanical behavior, and they use mechanical components to describe the complex viscoelastic behavior. So the first part of this, the spring, we've already seen and dealt with in terms of the linear elastic component of it. And this part of the material is not time dependent. So it doesn't matter what rate we apply the load, we're going to see the same type of response. It's a time-independent behavior. Our second component for these rheological models is a dashpot. And this is a schematic showing what the dashpot is, and the viscosity of this fluid here will change the response of the dashpot, how resistant it is to deformations. So a simplified example will be a bike pump, and I'll show how the bike pump works as a dashpot. So this is where we're going to get our time-dependent behavior. So for example, if we apply a force at a relatively low frequency, at a low deformation rate, we might have a stiffness that is shown here. And as we increase that loading rate, what we're going to see is the stiffness that we measure out will also increase. And so we can continue increasing our loading rate to get even greater stiffnesses or stiffness behavior. Essentially, if we load infinitely fast, if we're able to apply the force immediately, what we're going to see is a response where the force shoots up to infinity, theoretically. So this behavior is our time-dependent behavior response, our viscous response. So this is very important for describing the mechanical behavior of polymers as well as biological tissues. The viscosity of the fluid that's in our dashpot will change the overall behavior of our dashpot, how resistant it is to deformations that are being applied. So in this example, we have a fluid here. In the bike pump, we have air that is acting as our fluid. So you could imagine if in this dashpot we used honey that was at room temperature versus honey that we saw that was from the refrigerator, how different the material, the fluid material would be to deformations that are being applied.
Here I have a regular bike pump, which I'm going to use as a demonstration for how a dashpot would behave. So if I pull the bike pump up, it will drop down under its own weight. If I seal off this exit hole, you'll see that it does a better job of staying up, but there is still some weight to this, and you see it will slowly drop down. Now, if I apply a force, you see that it does it resists that push that I give it. So if I apply a force and hold on to that force, it'll eventually start to deform more and more as I keep pushing. Now, if I start at this initial spot and I try to move to a certain displacement, I won't reach it. Let's say I'm trying to initially go to a displacement all the way down to here. I try and I have to push really hard, and if I'm a machine, I don't reach it, and so I go back up to my spot, my landing spot. And that's why we see the infinite spike in the stress relaxation for the dashpot behavior when we're talking about the theoretical model for the dashpot.
So if we think about how the dashpot behaves over time, we can actually graphically show this. So at T equals T naught, and initially we have our dashpot with the plunger all the way into the fluid. If we apply a sudden force, and we apply a force and we hold on to this force, eventually our dashpot is going to displace. And so we see this with time, that there's a linear increase in our deformation with time. Eventually our plunger will move some distance here to T1. So as we hold on to this deformation and we keep it constant, it will stay there because there's no force pushing it back. It won't just drop down. Whereas in the bike pump example I showed, if we had this vertically, the weight of the plunger itself would allow it to move backwards in this direction. So that means I actually have to physically apply a force to my dashpot in order to create this movement of the plunger back into the fluid. And if I hold on to this force over a period of time, I'll see that the deformations will drop back down to the initial loading spot at T0. So in our rheological models, essentially what we're going to be talking about is how we can combine these physical models, these springs and these dashpots, to create models that describe the time-dependent behavior. So in all of these models, we're assuming one-dimensional deformations. And this is very important because we know that our materials have complex stresses involved with them and that they experience 3D deformations during loading. But we'll deal with that at a later point. So our first component for the spring, when we're doing creep or stress relaxation, we're going to have these equations that will describe this spring behavior, where I have my stress is a component of the strain that's being applied. And here I have Young's modulus E, and it's a linear relationship. And it's very similar to what we saw earlier, where we had F equals Kx, where F is the force and K is the spring stiffness and X is displacement. So all I'm doing here is going from force and displacement into stress and strain notation. And so in our creep, again, our spring response is going to be relatively boring to look at, where we have a flat response, a constant response with time. And this is similar for stress relaxation. So when we tell the input for the machine, the testing machine that we're doing, we're going to use a Heaviside function. And this Heaviside function means we're immediately going to our load or our displacement that we're applying and holding it there. This is important because the Heaviside function is something that we're going to use in theory. However, our testing machines are not capable of immediately jumping to our force or displacement. So in reality, we actually apply the stress at some kind of ramp, which is important for viscoelastic materials because depending on your capabilities of your machine, the ramp time here, there could be some time-dependent behaviors that are occurring, even though we're assuming it's an elastic response that will be occurring. So what happens with the dashpot as we apply displacement over time for creep and stress relaxation? So for the very fundamental building blocks of our viscoelastic models, our rheological models, when we apply creep, we saw this in the schematic a few minutes ago, where we apply the force and hold the force, we're going to have a linear response in our displacement. Our displacement will continue to increase over time. And then as we remove that force, or that stress, it will stay steady at that location. And so we can describe the stress on our dashpot as being a function of our loading rate, delta epsilon over delta T time, and a function of the viscosity of our dashpot fluid, eta. And so what you'll see here, and this is more important for the more advanced videos where we'll go through the deformations, is that we have a derivation here with respect to time. So if we solve for these things, we can solve for our strain with respect to time. And our initial condition, we can use our initial conditions to solve for C, and C is equal to 0 because at time equals 0, we know that our strain is also going to be equal to 0. So when we think about our dashpot in stress relaxation, where we want to move to a certain displacement initially, we're going to have an infinite resistance from our dashpot, theoretically an infinite resistance. And I like to think about this as our donkey here. If you try to pull and move to a sudden displacement, you'll have a lot of resistance. But if you apply a force and you hold on to that force, eventually the donkey will move along with you. So to summarize what we have in terms of our viscoelastic materials and how they actually typically respond in nature, if we look at creep versus stress relaxation, if we apply a force to viscoelastic materials, we typically see this response where there's an initial elastic response, and then we have this time-dependent response. where there's a gradual nonlinear increase in our displacement over time. And for stress relaxation, where we apply a displacement or a strain that we hold for time over time, we typically see a response where we have a peak stress, and this peak stress either eventually relaxes down to an equilibrium state, or it eventually relaxes down to zero stress conditions. And so this is typical of what we see in viscoelastic materials. So the next step for this is, how do we combine these springs and these dashpots in order to create mathematical models that describe this overall behavior of what we see in viscoelastic materials? And we'll cover the three most common viscoelastic materials in the next video, increasing in complexity as we move along from the first model to the third model.